Now that we have practiced how to find derivatives, and then in addition to that, how to use derivatives in order to find local maxes and mins, now we're going to talk about how we can apply those concepts to what's called optimization problems. And optimization problems are used to maximize or minimize something in the real world. In the business realm, we would want to maximize profit and minimize cost. So these are going to be mainly word problems, and the book offers a step-by-step guide on how to set these problems up. So let's walk through those, and then we'll use these steps to solve the examples I have. So step one, you want to draw a figure when appropriate. So if the question is talking about optimizing some kind of area, then you want to draw a picture of that area. A picture can really help you identify what variables you're looking for, what you know, what you don't know, what you have to substitute. It really does help, and it only takes a minute to draw that, so I really recommend that you do that. In step two, it says assign a variable to the quantity mentioned in the problem. So if there's any numbers or information given in the problem, label it as some kind of variable. So for example, if you're given the length of a table, then maybe you want to label L equals and then the length of the table. And number three, it says select the quantity that is to be optimized and construct a function that relates it to some or all of the quantities. So for number three, this is where a lot of people get in a rut. So at number three, what you want to do, if an equation is not given to you, you have to come up with one. So whatever it is that you're trying to optimize, you want to come up with some kind of equation that incorporates as much of the information as you can from the problem. Sometimes you can't, and you might have to substitute something in, and we'll go over an example of that. But you want to really pay attention to the question, what is it that you're trying to optimize? Meaning, what are you trying to find the minimum or maximum of? And then from there, try to set up an equation that involves that quantity with whatever you have in the question that's given to you. In step four, it says, since all the rules of differentiation deal with functions of only one variable, the function must involve only one variable. So if you have more than one variable in your equation that you're setting up, before you take the derivative, you want to make sure that you use any substitutions so that everything is in terms of one variable. Once you have your equation set up, then you want to take the derivative and then apply one of the derivatives tasks to that question. You also want to make sure in certain cases that you want to check for absolute maximums and absolute minimums. So here's our first example. Let's try and use the guidelines they gave us to solve this question. It says a rectangular region along the bank of a straight section of river is to be enclosed with 80 feet of fencing. Only 3 sides need to be fenced since the river will be bound on the other side. What are the dimensions that will produce the greatest enclosed area? So the first step in those guidelines is to make sure that we draw a picture. So here's our picture. We have a rectangular enclosed area, and then we have the river alongside of it on one side. And so we want to make sure that we maximize this area. So area is what is going to be maximized. So when we assign values, we have W for width, so that's going to go on each side, and L for length. The other variable that's given to us, but not shown in the picture, we're also given that we have 80 feet of fencing. So that means all of these three sides, if we want to use all the fencing to maximize the area, these three sides added up, the length should be equal to 80. So off to the side on your paper, you might want to also add in there the perimeter is equal to 80, and you can label that however you want. I would personally put in P is equal to 80 feet. For step 2, you want to make sure you label everything. So we started talking about it in step 1. We're going to label the area that we're trying to maximize as A, the length is L, the width is W, and then they labeled it P as well. That would be my first preference. But so you want to take P and set it equal to 80. That's your perimeter. In step 3, you want to identify what's to be maximized or minimized. In this question, we're trying to maximize the area. So because we're trying to maximize the area, we want to make sure we come up with an area formula. So to find the area of a rectangular region, using the labels on the previous page, we have L times W, length times width. So, and there's a little note here too, that the area depends on the length and the width. Part 4 was we need to make sure that we only have one variable in this area equation before we try to take the derivative. So what we want to do is use some other information given to us in the problem to make a substitution. So because we know that the perimeter is 80, and this part is a little bit tricky because we normally think of the perimeter of a rectangle as 2 widths and 2 lengths added up. But because we're not using the side by the river, we only have 1 length and 2 widths. So we're going to set up the perimeter equation as L plus 2W is equal to 80. That's the total fencing we have. Now, the author of the book decided to solve for L. If you decided to solve for W instead, that's totally fine. You'll get the same answer in the end. You just want to make sure you have your area function in terms of one variable. So the author of the question chose to solve for L. So in this equation for area, we're going to substitute L for 80 minus 2W. So now I have the length, which is 80 minus 2W, times the width, which is W. And now we have a function here in terms of just one variable. So area now, the way that we have this set up, is only dependent on W. All right, so let's go to the next slide. So now that we have our area defined and we have a function for that, now we go and take the derivative. Now, we had 2 equations in this problem. We had the equation for the perimeter, and we had the equation for the area. Because we're trying to maximize the area is what we need to take the derivative of. So I take the derivative of the area, and I get 80 minus 4W. So if we use the first derivative test to find our local max, then we want to take the first derivative, set it equal to 0, and find those critical values. And then once we find those critical values, we want to make sure that we're creating a sign chart so that we can put in our pluses and minuses on the intervals where it's increasing and decreasing. And so once we do that, we can identify local maxes and local mins. So when we set that area, the derivative of the area equal to 0, and we solve for W, we get 20. We have one critical value so far. We have that W is equal to 20, and that's what we got when we set the derivative equal to 0. The other places where we could get a critical value is when the derivative is undefined. But because this is a polynomial, we don't have to worry about that in this case. So once we find our critical values, we can check the sign chart to verify that it's either a max or min, whatever we're looking for. In this case, we're looking for a local max. So I suggest, even though the author of the book didn't do it here, that you use a sign chart to check to make sure that it's a local max, or you could look at the graph and make sure that it's a max, whatever we're looking for. In this case, we're looking for a local max. So I suggest, even though the author of the book didn't do it here, that you use a sign chart to check to make sure that it's a local max, or you could look at the graph and make sure that it's a max. And then the last thing you want to do is check for absolute mins and maxes. So because we could have an absolute max that's larger than our local max, we want to check our endpoints as well. So maybe we have an interval that looks like this. So we have our local max here, but maybe our absolute max at the endpoint is bigger. So that's why we're checking these endpoints. So we want to plug in 0 and 40 and see what that yields. We get that when we plug in 0 for the area, we get 0. When we plug in 40 for the area, we also get 0. But when we check our critical value and we plug that in where we think our local max is, we get 800. So this is definitely the bigger of these two. Now, just to clarify, because this picture does not look like what this example is supposed to look like, I was just giving this as an example of what could happen. So in our case, we have a parabola. Let me actually draw what our graph looks like. We have a graph that looks like this. If this is 0 and this is 40, and we have 20 in the center, here's our y-axis. Our graph looks like this. So x0 at 40, x0, x0, although it's not really lined up very well because I'm writing with a mouse right now, but hopefully it's clear enough that you can read that. Here's 20, and we have our maximum at 20. So because we now know that our W for the maximum is 20, and we know that L, the length, is 80 minus 2W, we can find the length by plugging in W for 20, and we get the length is 40. So that means that in order to maximize the area, and our maximum area, because we plugged it into check, is 800, and this was in feet, so we would have 800 feet squared. Our length would have to be 40, and our width would have to be 20. Okay, so here's the official interpretation. The dimensions that produce the maximum enclosed area for 80 feet of fencing is a length of 40 feet and a width of 20 feet. That's given by this formula here, A of W. That's the area in terms of the width. And it reinforces the fact that absolute maximum area occurs when the width is 20 feet. So here's the picture that I just tried to draw on the previous slide. It's a much better drawing. Here's our maximum area, and this is at 20 feet for the width. And then we used our formula of the perimeter. We know that the perimeter is equal to 2 widths plus 1 length, and so we know the perimeter is 80. We know that our width was 20, so we have 20 times 2, which is 40, so the length would have to be 40. So this might come in handy to understand how to do this if you were a farmer or a real estate agent that needed to maximize some area of land. Let's look at our second example. We have the concentration, C, of a drug in the bloodstream T hours after it's been administered is approximated by the function below, and the concentration is given by milligrams per centimeters cubed. So here's our formula for concentration, and T represents the number of hours, and we have 7T over T to the third plus 18. And we're only going to be looking at this when T is greater than or equal to 0, because it doesn't make sense to talk about negative time. In this example, there really isn't any picture that we can draw that will represent this situation other than maybe the graph. There's no geometric shapes in the context of this problem that we would want to draw and label. We can go right to taking the derivative, and we're going to use the quotient rule. So we're going to take the derivative of the top, which is 7, and multiply it by the bottom, which is t to the third plus 18. And then we're going to subtract the derivative of the bottom times the top. Here's the top, 7t times the derivative of the bottom. The derivative of the denominator is 3t squared. So that goes here. And then we're going to write that all over the denominator squared. Now, after we multiply out across the top and combine like terms, we get that we have 14 times 9 minus t to the third all over t to the third plus 18 squared. So the next step is we want to find our critical values. So that's where the derivative is either equal to 0 or where it's undefined. So we're going to look at where the derivative is 0 first. So in order for a fraction to be 0, the top needs to be 0. As long as the bottom isn't 0 at the same time, we can just look at the top. So I'm going to set the numerator equal to 0, and when we solve, we get that t is the cube root of 9. Now, to find any other critical values, we want to look to see where the derivative is undefined, and that's what makes the denominator 0. Now, the denominator was t to the third. Let's go back. T to the third plus 18. What makes the denominator 0 would mean that t has to be negative. We would have to plug in a negative number, cube it, and then add it to 18 to get 0. So since we're only talking about values of t that are positive because we're talking about time, we're not concerned about the t that's negative. So that means we're only going to be looking at this critical value here. Now, if it wasn't in the context of this problem, we would definitely want to make sure that we look at that critical value. But because this is in the context of a problem where we're only looking at positive t's, then we don't have to worry about that. If we look at the graph, we have this shape here. Since we're looking at this over the interval greater than or equal to 0 for time, we're going to keep going out this way for our interval, but we're going to start at 0. And as you can see, 0 is our absolute min. But because we're looking for a maximum for this problem, we're going to stick with the cube root of 9. And that approximation in decimal form is 2.08. So by looking at the graph, we verified that that's a maximum over that whole entire interval. We checked our endpoints by looking at the graph. This endpoint is 0, 0. We don't really have an endpoint going to the right. So now let's interpret everything that we've just looked at. The concentration of the drug is maximum when it's 2.08 hours after the drug is administered. And we also brought up the fact that the minimum value was here at 0. So the concentration begins at 0 when it's administered, and then it climbs quickly, reaches its max, and then it starts to level off as time goes on. We have one last problem to go over, and in this example, we are going to create an open top box using a piece of cardboard that is 10 inches by 16 inches. And the question is asking us to remove small squares of equal size from the corners and then fold up the remaining flaps that would create the box. Now we want to find the size of the squares that we need to cut out in order to maximize the volume. And we need to find the size of the squares that we need to cut out, so we will create a box with the largest possible volume. So we're trying to maximize the volume. So using the guidelines, in this case, we do have a picture that we can draw. So here's our picture. Here's our piece of cardboard. Then we cut out the squares in the corners, and we fold it up along these dotted lines to create our open top box. Okay, step 2 is to label all of our variables. We're going to label the squares that we cut out of dimensions h by h. Now they're going to be the same because they're squares, and the author of the book is labeling it h because, let me go back another slide. Let me go back a slide. These are the dimensions right here that where my laser pointer is that we're going to cut out. When we fold it up, that length and width of the square that we cut out is going to be the height of the box. So the author of the book decided to label that square with dimensions h by h because that h is going to end up representing the height of the box. Now, when we look at the length and the width, let's look at the width first. Since we're cutting out these two corner squares and they have dimensions h by h, that means this length right here and this length right here is a length of h. So we could describe the width of the box by taking the entire width and subtracting 2h. That would be our w. And then we're going to apply that same idea to the length. The entire length before we cut out the squares is 16. When we cut out the squares, what's left, which is going to be the length of the box, is going to be 16 minus this h and this h, so 16 minus 2h. And then we're going to label v for the volume. The next guideline, step 3, is we need to come up with an equation that relates what we're trying to maximize or minimize to the other variables. Since we're trying to maximize the volume, we need to come up with an equation for the volume. Based on the variables that we set up here, we have that the volume of the box is length times width times height. However, if you notice, we have multiple variables in this one equation, and that would be step 4, when we have to rewrite everything so that it's in terms of one variable, so it's easier to find the derivative. Since we set up that the length was 16 minus 2h, and the width is 10 minus 2h, and we have in the formula length times width times height, if we replace w with 10 minus 2h, and we replace length with 16 minus 2h, and we substitute that in, then we have everything in terms of h. If we multiply it out, we get 160h minus 52h squared plus 4h cubed. So that is our equation that we need to take the derivative of now that we have everything in terms of one variable. When we take the derivative, we get 160 minus 104h plus 12h squared. Now we need to find the critical values. The critical values is where the derivative is equal to 0 or where it's undefined. Because this is a polynomial, we don't have to worry about anywhere that it's undefined. So we can just set this equal to 0 and we'll have all the critical values we need. Because this is a quadratic, we can either use the quadratic formula, we can factor, or we can use complete the square method. My personal preference, if given the choice, I like to factor. Another thing that is my preference is before I do anything to solve a quadratic, I like putting it in descending order. Even though the author of the book did not write it in here, it might be a good idea to make a note off to the side to write this in descending order. You can factor out a 4, and then you have 4 times 40 minus 26h plus 3h squared is equal to 0. And then if you divide both sides by 4, you're essentially getting rid of a factor that we don't even need. Then we're left with 40 minus 26h minus 3h squared is equal to 0. And then when you factor, you get 3h minus 20 times h minus 2. So you have to set each of these factors equal to 0 and then solve for h. And when we do that, we get 20 over 3, or we get 2. Now, this here, this height 20 over 3, we can actually omit that from the question. And the reason is because if I take 20 divided by 3, that is going to give me 6 2/3. But if we go back and look at our picture, the height has to be under 5, because if this is 5 here and this is 5 inches here, and this is 10 inches, then there's no middle part to create the box. So we need to keep that height under 5 inches. So now we're just looking at a critical value of 2. You can either use a sign chart or look at the graph to verify whether 2 is a local max or local min or neither. Now, in this case, we're using a sign chart, and to the left of 2, it's a positive, meaning the function is increasing on that interval, and to the right of 2, it's negative because the function is decreasing on that interval. So that means if it's going up and then coming down, this 2 represents a local max. Because we're using this open interval, we want the height to be greater than 0. If we have a height of 0 and we make that as part of the interval, then we're not going to have any square to cut out in order to fold up the boxes, which doesn't jive with what we're trying to do here. And we don't want to include 5 because if we create 5 as our endpoint for the interval to check for an absolute max, then that's not going to make sense either, because then when we cut out a 5 by 5 square on either end, that's not going to leave any room for a width of the box. So in this case, checking the endpoints for a maximum really doesn't make sense. Now, if you didn't catch on to that, and you actually plugged it in to check it, when you did plug it in, you would have realized that this doesn't make sense. So if you do that, it's not a big deal. It's just an extra step. So now that we know 2 is a local max, and it's going to be the point on that interval that's going to work for us for what we're trying to do, we want to say that the squares that we're going to cut out is going to be 2 inches by 2 inches, and that's going to maximize the volume. Now, if we want to go find out what that volume is, we would have to go back to the volume equation and plug in 2 here to see what that is. Now, I want to use that question we just did with the box to show you how you can find maxes and mins on GeoGebra so you can check your work. So I have our volume function preloaded from the previous example, and I scaled the graph so that we can see all the major features of the graph. And if you're not sure how to scale it, because I can't remember if I showed you this or not, if you need to scale your axes, you come over here to this little gear, and you go to settings, and then under basic, you can set your X min and max and your Y min and max. Now, once you enter your function to find your special points, as GeoGebra calls it, if you click on this here, special points, so click on those 3 dots there and choose special points, all of those major points on the graph will come up here. It's basically going to be your roots, which are the values of X that make that function equal to 0. Sometimes they can be complex, but if they're real numbers, you'll see them show up here on the real plane. So we have our x-intercepts, 0, 0. If you click on it, it will show you the value, 5, 0, and 8, 0. So those are your real roots. Then for your local mins and maxes, that's listed under here under extremum. So if you look, point D that's labeled, that's 2, 144, that's up here. That's our local maximum. And as we determined previously, we know that when we cut out a square that's 2 by 2, that's going to give us a maximum volume. But on here, we can actually see what that maximum volume is. It's 144. And I think we were doing this in terms of inches, so that would be 144 inches cubed. Now here's our local min. That's this point here that's labeled as E. Although it shows up on the graph and it is a local minimum on the graph, we did not consider this point in our question because it didn't make sense to go outside the length and the width of the square outside the interval of 0 and 5. We wanted to keep it within 0 and 5. So GeoGebra can be a nice tool to check your work when you're doing maxes and mins as well. But just keep in mind, you need to show your work for this, but you can use GeoGebra to check it to make sure that you've got the right answer.